To begin with, we have an exciting and insightful session on machine learning algorithms. It is my honor to introduce Dr. Ipshita Nanda, Professor and Dean in the School of Computer Science and Engineering, IILM, University, Greater Noida, UP. She did her doctorate from the Center for Advanced Postgraduate Studies, Biju Patnaik University, and she has over 20 years of experience in teaching, research, and administration. Her area of research is system on chip design, Internet of Things, artificial intelligence, machine learning, automation design, data science, and she has published 67 research papers in SEI, Scopus, Web of Science journals, and international conferences. She holds 25 granted patents and 10 copyrights in different fields of research. She has also received the Best Paper Award and trophy for her research work. And today, Dr. Ipshita Nanda will walk us through the core machine learning algorithms about supervised and unsupervised learning for load forecasting. So without any further delay, let's welcome Dr. Ipshita Nanda for their session. Over to you, madam.
Thank you so much for inviting me. And it's an honor that I'm always connected with AIMA Association and this time with Heritage Institute of Technology. So let me start my talk. And thank you so much for inviting me. Kindly allow me for presenting it. Yeah. Hope the presentation is visible.
Yes, madam.
Yeah. Thank you so much. So as we are in the world of AI ML, and these days market is like we are integrating everything, right? So integration means what now? As you can see that we are integrating electrical engineering with the combination of computer science, that is load forecasting is the electrical area. So supervised unsupervised is now is an algorithm where we can utilize over uh, each and everything, you can say, right? So that is what the magic of AI ML, and we are like looking forward that why not to implement, why not to integrate it, right? So that is what, and in every case we should see that how this algorithm will be helping us in each and every areas. So so that all of us, not only computer science, because everybody is thinking that this is a computer science topic. No, it's not like that. It's like we can say that is now implemented in electrical, electronics, computer science, everywhere it is implemented. So now we are integrating it, and we can see that how this integration will be helping us in the future. So load forecasting, let us go from back to front. That is, let us now understand that what is load forecasting. So load forecasting as a whole, if you can see that, uh, just a minute. Yeah. Hope I'm audible.
Yes, ma'am.
Yeah.
Yes, ma'am.
Yeah.
Let me increase it. Yeah. So as load forecasting, if you can see that it is a very critical process, right, in the energy sector, and we are aiming towards the prediction of the future electricity, which demands to ensure a stable and reliable power supply. So accurate load forecasting that supports efficient grid management, resource planning, and operational decision making. So like we can see that traditional method, if you are going for, like, because we need to integrate the traditional as well as the modern, right? Because modern technology means we are integrating machine learning, that is supervised unsupervised algorithm. But in case of traditional method like regression and ARIMA, which has been widely used But in case of machine learning techniques, we can use both the supervised as well as unsupervised, because these days it is gaining prominence due to their ability to handle complexity, we can see, non-linear patterns, we can see, and adapt to, like, dynamically it can adapt, right, to the changing environment or changing requirement or changing the conditions. So by leveraging the historical data, weather conditions, and other relevant features, machine learning models can provide more accurate and scalable solution for load forecasting and across different time horizon. So why machine learning is like utilized in case of load forecasting? Because we can see that in case of traditional methods like regression and ARIMA, as I told, that is like we are dependent on the time horizon, with short term, that is like minutes to days, right? Or we can see medium terms, that is weeks to month, okay? Or long terms, we can say from months to year. So this is the way I'm giving the example of the machine learning models that can capture the integrate dependencies of data, we can see, right? Because like sort forecasting benefits, all these things we have to think about. Like traditional method, we have taken regression, ARIMA. ML benefits, like it can handle the complex non-linear patterns and adapts it dynamically. So here we can say that machine learning is having the flexibilities which is allowing it to adapt to these varying requirements and making it powerful tool to modern energy systems. Like for example, I have given that is the forecasting time horizon, that is like medium terms, short terms, long terms, right? Because for instance, we can see that short term forecasting benefits from real time adjustment, right? While long term forecasting requires understanding broader trends influenced by the factors like economic growth or seasonal changes. So one by one we have to take, that is like first of all we have to focus on the short term goal, then we have to go for the medium term, and then we can go for the long term. Now what are the data requirements of the load forecasting? Like you can see over here, historical load, weather, holidays, weekends, industry, demographic profile. Now what is this, the meaning of this, right? Like high quality data is the foundation of effective load forecasting. Key data inputs include historical data records and weather condition like temperature, humidity, etc. Calendar effects like holidays, weekends, versus uh, we can take one by one, right? And the broader demographic or industrial profiles. So weather data is particularly crucial Weather data is particularly crucial as it is directly impacts electricity consumption. Additionally, incorporating, we can say that it is a temporal features like time of day or day of the week, which helps the model to capture and ensuring that the data completeness, accuracy, and relevance is essential for training robust machine learning models. These all are the things which are very much essential, and we are very much dependent on this.
Ma'am, you're on mute.
So in every cases, like, sorry, it was muted. I'm very sorry. Uh,
Yes.
so relevance is essential for the training robust machine learning models. So in case of supervised, now moving towards, like we can say that moving towards the learning that is like modern technology and all, and we have left behind the traditional technique. Now why supervised learning, why this, and where it is utilized, right? In case of supervised learning, you can see that it's a machine learning, right? It's a machine learning, nothing else, where models are trained on the labeled data. Which data? Those are the historical data. Now, what is the historical data? Because the data which we are collecting from environment, that is known as raw data, not historical data. Now, we have to compare the raw data with the historical data which were previously collected, right? So that we can predict the outcomes. So the goal is to learn, like we can say that mapping between the input features, that is weather and time, and known as the output values, for example, electricity and demand. That is the approach which is widely used for the forecasting due to its ability to deliver precise prediction where sufficient labor data is available. So common algorithm, let us take linear regression, decision tree, and the neural network, right? These are the common algorithm which are, like we can say that linear regression, that is for the baseline models, support vector machines for the handling the non-linear relationship, random forest for ensemble based prediction we can say, and neural network which is very common these days, very demanding for capturing deep complex patterns, that is like from data. If we cannot identify, then we always utilize the neural network. Now, in case of supervised algorithm, as we are known, like we are aware of linear regression, support vector machine is always known as SVM, random forest, SGBoost, right? Neural network. So most common is the linear regression, then SVM, and the neural, that is NN. Neural network is otherwise known as NN. Now, several supervised learning algorithms are particularly effective for load forecasting. That is like linear regression, if you are taking, then it provides a simple yet interpretable baseline. While SVM, that is a support vector machine, excel in high dimensional spaces. Random forest and XGBoost, that is leverages ensemble technique to improve the accuracy and robustness by combining the multiple decision trees. And neural network as a whole, which I told that is very famous and very much utilized in case of research, that is especially for the deep learning architecture, which are very powerful for modeling nonlinear and temporal dependencies and making them suitable for tasks like hourly load predictions. So these are the choices which we need to make, that how to specify it and where to utilize it, right? So the choice of the algorithm depends on the problem complexity, data availability, and computational resources. So this is how, right? And this is why we are utilizing it. So the case study over here, that is of supervised learning, we will be doing also one because the time, if the time permits, we will be doing one example over here, so that FDB will be fruitful as a whole. I think that if some hands-on practice will be there, then it is beneficial. For that reason, I will be opting it if time permits. So a practical example of supervised learning, which is taken over here in load forecasting, involves using a random forest model, which is trained on the historical hourly long data alongside weather features, right? So the model task is to predict electricity, which demands 24 hours ahead, right? So by taking these features like temperature, humidity, time of the day, the model can learn the relationship between these variables and the load pattern. So the result demonstrates how supervised learning can achieve high accuracy in long-term forecasting, and we can enable or utilize to optimize the generation and distribution. So a Python implementation using the libraries like scikit-learn, which can be explored in the provided Google Colab notebook. So supervised learning pros and cons, like we can say that if you are taking something into consideration, that is supervised learning, that is advantages and disadvantages. Advantages are like it includes high accuracy, where label data is abundant, and the ability to incorporate diverse input features like weather and calendar effects. So, however, it also has only the limitations, that is like there is a need of labeled historical data that is having some constraints, as acquiring and cleaning such data is often resource incentive. That is, additionally, supervised models are prone to overfitting. So, especially with complex algorithms like neural networks, which requires careful regulation and validation. So, despite of many challenges, supervised learning remains a cornerstone of load forecasting due to predictive powers, right? So, all these things, like if you are having some advantages, if you are having some disadvantages. If there are challenges, then only there is a possibility of improvement, possibility of research, right? So that's what we should always see, always stand with the challenge. But it's like unsupervised algorithm. Like unsupervised means what? There is no supervision. There is no one to supervise it, right? So we need to see that how the patterns will be recognized, how the structures will be formed, so that we can identify the hidden uh, patterns, right? Hidden areas, we can see hidden areas where we are not able to find the like we are not going to any conclusion, and that is the thing, so that the analysis will be properly done by the identification, right? Pattern identification is some features are identified, then we can identify the pattern. That is what is the uh, we can say that is whole about unsupervised learning. That is, there is no supervision, there is no one to supervise. So in case of this, like if you are taking the example of load forecasting, then unsupervised techniques like clustering, anomaly detection, and we can say that dimensionally reduction in load data, all these things are required. So for example, let us take like k-means clustering, which can group the days with similar electricity consumption pattern, such as weekdays versus weekends, while principal component analysis, that is PCA, popularly known as PCA, which can reduce the data dimensionally to highlight the most influential features. So these methods are particularly useful when label data is scarce or when exploring unknown pattern in the data. Unsupervised learning algorithm, all we all are aware, that is K-means clustering, hierarchical clustering, PCA, then autoencoder. But now the meaning of this and why it is utilized specifically in this case. So in case of we can say key unsupervised learning algorithms for load forecasting, which includes K clustering, which partitions the data into distinct groups based on the similarity. And if you are taking like hierarchical clustering, then which builds a tree-like structure of data relationship. And if you are taking PCA, which is widely used for dimensionality reduction, that is like simplifying the data set while preserving the critical information. And as a whole, if you are taking the last one, that is the autoencoders, that is a type of neural network which can be employed for feature extraction and anomaly detection by learning complex, or we can say that compressed representation of the input data. So these techniques that enable utilities to gain insights into consumption behavior without relying on pre-labeled dataset. So let me again repeat it, because it's something different. That is, K-means clustering. Why it is utilized for the partitioning the data into distinct groups based on the similarity. If you are going for the hierarchical clustering, which builds a tree-like structure of data relationship. If you are taking PCA, then that is like we are dimensionally clustering, we can say it is dimensional reduction, right? So simplifying the data set while preserving the critical information. Autoencoder, if you are taking like it's like we can say that it's a type of neural network. Please remember this, it's a type of neural network which can be employed for feature extraction and anomaly detection by learning compressed representation of the input data. So these are the things uh, because of which we are utilizing this particular algorithm in case of load sharing, right? Load forecasting. So in case of like supervised learning, if you are taking, like in case of supervised learning, if you are considering, then we need to see that how supervised models are trained on historical load data with corresponding features like weather and time. So they are effective for the short term and medium term load forecasting due to their accuracy. For example, like as I told that neural network to capture nonlinear relationship in the load pattern. Now, in case of case study, as I told that we will be doing this. So for that reason, I have taken this one. We will be doing this. No worries. Let us first conclude the theoretical part. That is like unsupervised and supervised learning case study. Like let us move to unsupervised case study. That is like here also we have taken daily load curves, that is 24 hours pattern per day. Then the model which we have taken, that is k-means, the output over here, that is cluster of similar load behavior days, and the Python code we will be doing it. So here an example of supervised learning in Exen involves like applying k-means clustering to daily load curves, right? That is 24 hours consumption patterns for each day. So the algorithm groups the days with similar load profiles and such as like distinguishing weekdays from weekends or identifying the holiday patterns. So this segmentation over here can inform tailored forecasting model for different day types and improving the accuracy. So the Python code which is taken as an example in the Google Colab demonstrate that how to implement k-means clustering and visualize the results, showcasing its practical utility in the load sharing or load forecasting, load forecasting. So unsupervised learning in load forecasting is like we can play a complementary role to supervised methods, right, in load forecasting by identifying the inherent patterns, seasonal behaviors, and anomalies in unlabeled data, right? Unlabeled data and unsupervised techniques enhance the overall forecasting process. For instance, if you are taking like we can say that clustering can segment customer or region with similar consumption behavior and bringing like we can enable targeted demand side management, right? So anomaly detection which helps the flag unusual consumption patterns which could indicate equipment failure or fraud. So these capabilities make unsupervised learning a valuable tool for doing some analytical work and pre-processing before applying the supervised learning. So this is like we can see that is an how the supervised, unsupervised learning techniques are applied for load forecasting and highlighting their respective strengths, challenges, and real method or real world application, how it is connected, right? So by combining these approaches, what happens? Energy providers can build more robust and accurate forecasting to meet the demand of modern power grids. Now, what are the advantages of supervised learning for load forecasting? Like we can say that supervised learning offers several compelling advantages for load forecasting. Like particularly when high quality label data is available. So these models they excels in accuracy. First one, as they are trained on historical data, whether the actual load values are known or not known, allowing them to learn precise relationship between the input feature like weather condition, time, or time of the day, let us take, and electricity demand. So additionally, supervised models can incorporate like a wide range of relevant variables such as temperature, holidays, economic indicators to capture the multifaceted nature of power consumption. So their adaptability, which makes them suitable for various forecast horizons. So like we can let us take like from hours to day ahead, right? That is like hourly prediction to longer term estimates spanning days or weeks. For example, neural network that can bring some complex models, nonlinear dependency in short term load fluctuations, while ensemble methods like random forest which provides robust medium term forecast. So the ability to evaluate the performance using matrices like MAE, RMSC, which which further ensures that these models can bring fine tune for optional results. Now, what are the advantages of unsupervised learning for load forecasting? Like we can see that it is bringing a unique strength to load forecasting, especially in a scenario where labeled data is scarce or costly to obtain. Right. So by analyzing unlabeled data, these techniques uncover hidden patterns, hidden structures, such as like recurring consumption patterns or anomalies with or without relying on the predefined outputs. For instance, clustering algorithms like K-means that can segment days with similar load profiles, right? That is, for example, weekdays versus weekends. That is like we can enable utility to tailor forecasting models for distinct groups. So in case of unsupervised methods, also we can utilize anomaly detection, identifying irregularities like sudden spikes or drops in demand that may indicate equipment failure or fraud. So furthermore, dimensionality reduction techniques like PCA will simplify the data set by extracting the most influential features. So that is like improving computational efficiencies. So these capabilities, you have to understand this part. That is like these capabilities makes unsupervised learning invaluable for the analytical or pre-processing work or laying the groundwork for more targeted supervised model or standalone applications in grid management. Now, what are the evaluation matrices? Like as I told that MAE, that is mean absolute error, RMSE, that is root mean square error, MAPE, that is mean absolute percentage error, right? So in this case, supervised, that is MAE, RMSE, MAP, MAPE, okay? And unsupervised Killerty score, Davis-Walton index, okay? All these things we are taking. You can see in the block diagram that is evaluation matrices, MAE, MSC, RMSC, R squared, adjusted R squared, supervised accuracy, precision, recall, F1 score, specificity, and unsupervised RAND index, adjusted RAND index. That is, all these things are we are taking into consideration, right? So if we are taking this, we need to understand the specific meaning. In case of evaluation matrices, that is like evaluating what? Evaluating the performance of whom? Of load forecasting models, which requires distinct matrices for supervised and unsupervised approaches. So for supervised learning, common matrices include MAE, okay, which measures average prediction error in absolute terms. RMSC, if you are taking, which penalizes larger errors more heavily. MAP, that is which expresses errors as percentage of actual values, aiding many constraints, right? So these matrices helps to assess how closely the prediction can be aligned with the observed data. So in contrast, unsupervised, if you are taking, it relies on the matrices like Skill-Horty score, which quantifies how well data point fits within this cluster, and Davis-Walton index, which evaluates the cluster separation and compactness. So these matrices that clustering or bringing some dimensionality reduction technique and effectively reveals the meaningful patterns. So selecting the right evaluation criteria is very critical for model validation, optimization, and we can also take comparison across different methodology. So all these things now will be done through the tools and the libraries, right? Because without tools and libraries, nothing can be done. So implementing machine learning for the load forecasting is facilitated by a robust ecosystem of tools and libraries. So in Python, popular choices include scikit-learn for classification algorithm, right? Like regression and clustering. TensorFlow, if you are taking, that is for the deep learning. TensorFlow and Keras. Also, we can say for deep learning models and specialized libraries like SGBoost, right? For gradient boosted trees. So let us go to R now. R uses often leverages the package such as Caret, CARET, for unified modeling workflows and forecast, that is for the time series analysis. So cloud platforms also required because we need to store, right? So like AWS forecast, Azure ML, everybody must be aware of this, which provides scalable end-to-end solutions with built-in automation for data forecasting, right? Or we can say data pre-processing, model training, deployment, right? So these tools, they bring the access, or they give the access to advanced machine learning capabilities, enabling utilities and researchers to focus on refining the models rather than infrastructure, right? So open source notebooks such as Google Colab further lower the barrier to entry by offering the scalable, executable code example for both supervised and unsupervised algorithms or techniques. Now, what are the challenges of using the machine learning for the load forecasting? Despite of its many potential, machine learning for load forecasting, that is faces several challenges. Data quality and quantity are the paramount, right? Incomplete, noisy, or non-representative data set can undermine or model performance. Overfitting, that is another risk, right? So particularly with the complex algorithms like neural network, where models may memorize training data, which include generalizing to unseen scenarios. So interpretability also remains a hurdle, as stakeholders often require transparent explanations for forecast, which can bring conflict with the black box nature of some advanced model. So integrating domain knowledge, such as understanding how industrial activity or like weather extremes affect the demand. So it is very essential to bridge this gap, right? Because we need accurate and robustness. These two are the features which is very much necessary. So additionally, if you are like related to the real world deployment, that must have some account for dynamic condition like sudden weather changes or economic shift, which requires models to adapt continuously, right? So that is the uniqueness which we need to study also, we need to analyze also. And there is a challenge. Unless and until you are aware of this, then how you will be doing improvement in that area? So addressing these challenges demands a balanced approach, combining robust data pipelines, model regularization, and collaboration between data scientists and data experts. So future trends in load forecasting with machine learning, that is like we can see that the future of load forecasting lies in innovative hybrid approaches, right, and cutting edge technology. So hybrid model, if you are taking, that combines the supervised and unsupervised learning, which are gaining the transaction, right, which are gaining the transaction, leveraging the strengths of both. For example, using clustering to segment data before applying supervised models for each segment. So deep learning architectures such as transformer networks, which are being explored to capture the long-term dependencies and complex temporal pattern in the load data. So the integration of real-time data streams from IoT devices and smart meters promises to enhance the forecast accuracy and responsiveness, enabling the utilities to react dynamically and to demand fluctuations, right? So edge computing could further decentralize forecasting and bringing computation closer to data sources for faster insights. So as renewable energy adoption grows, models must also adapt to volatile, we can say volatile of solar and wind generation. So making probabilistic forecasting and uncertainty qualification increasingly important. So these trends underscore a shift towards more adaptive, granular, and integrated forecasting systems. Now the conclusion and the key aways, like we need to know that what is the key takeaways of this total thing, right? So in summary, like we need to summarize somewhere, that is supervised and unsupervised learning, like each plays vital role in modern load forecasting. So supervised learning, which excels in delivering the precise prediction when labeled historical data is available and making it ideal to for short to medium term forecast. So unsupervised learning, on the other hand, science in uncovering hidden patterns, segmenting data, and detecting the anomalies. So even without labeled outputs. So combining these approaches, which can yield which can make more robust system. For instance, using clustering to identify, we can say that distinct demand uh, profiles before training the specialized models for each clusters. So combining both the approaches can lead to more robust and accurate load forecasting systems. So as the field evolves, we need to embrace the hybrid models, real-time data, and domain expertise, which will be bringing the key to addressing the challenges and unlocking the new opportunity in the grid management and energy planning. So this is the conclusion.